Let's do another summation problem. The summation problem that I want to do is the sum as n goes from 1 to some number k of just n. Right? In other words, I want to add up 1 plus 2 plus 3 dot 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 plus k. Right? I want to add up the first k whole numbers. These are called triangular numbers. The reason is because performing this sum is really counting the dots in a triangle. Let me draw a picture. So 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, right? And then I'll keep on going until I get to k dots. You know, and this picture here is a triangle, right? So this sum is counting the number of dots in a triangle. Having that k there makes this a very general problem. And any time that you're confronted with a general problem, it helps to specialize to a specific case in order to gain some insight. So let's set k equal to 10. So I'm just going to do the sum, n goes from 1 to k, which is now 10 of n, which means I'm going to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. I could actually draw this as a triangle. Put down 1 dot, 2 dots, 3 dots, 4 dots, 5 dots, 6 dots, 7 dots, 8 dots, 9 dots, 10 dots. Okay, so I've got this triangle, and this sum is just the number of dots in this triangle. Now I just count those dots, or just add those numbers up. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, 15 plus 6 is 21, 21 plus 7 is 28, 28 plus 8 is 36, 36 plus 9 is 45, and 45 plus 10 is 55. So the sum of the first 10 whole numbers is 55, and I drew 55 dots to make this triangle. But there's another approach. Instead of just adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, I could add these in a different order. I could add 1 and 10 together to make 11, 2 and 9 together to make 11, 3 and 8 together to make 11, 4 and 7 together to make 11, and then I'm left with 5 and 6, and those two together make 11, right? So I've got 5 groups of 11, which means if I add up all these numbers, I get 55. Armed with this trick, I can do the same thing to attack the problem in general. So in general, I'm trying to do the sum, n goes from 1 to k of just n. I'm trying to add up the first k whole numbers. And if I write this in a different order, and let's say k is even, just to make this a little bit easier to think about, right? I'll take the first number and the last number and add those together, the second number and the second to last number and add those together, the third number and the third to last number and add those together. And I'm going to keep on going, right? And the first number and the last number is, I'm writing it as 1 plus k, that's fine. The second number and the second to last number, well, that's also 1 plus k. All right, the third number and the third to last, that's also 1 plus k, right? All of these things add up to 1 plus k, and the key question is just how many things I've got, right? And I'm pairing them off in twos, so let's say this is an even number, k is an even number, then I've got k over 2 pairs, all of which add up to k plus 1, and that's just a multiplication problem, right? That means that this sum is 1 plus k times k over 2. So that's the sum of the first k whole numbers. If all this algebra doesn't really speak to you, we can redo this geometrically. So what I want to calculate, right, is this sum. The sum as n goes from 1 to k of n. And geometrically, right, I can draw this pattern of dots, right? 1 plus 2 plus 3 plus 4 plus 5 plus 6 in this case, but I could imagine that, this is a specific picture that represents the general case, right? I've got this triangle, a k by k triangle of dots, and this sum is just counting the number of dots, right? 1 plus 2 plus 3, that's exactly what this sum does. Now I want to count these dots, so I'll make 2 copies of this picture. So now I've got 2 copies of this sum, right? This is another k by k triangle of dots. And to count these dots, I'm going to take this triangle, rotate it, and slide it over here so as to make not a k by k squared, but this is a k plus 1 by k rectangle. Right, because the bottom of this one just sort of fits in and makes it a little bit wider. I've got this k plus 1 by k rectangle of dots. So I know there's k plus 1 times k dots, and this is 2 copies of the sum that I'm interested in. So 2 times the sum I'm interested in is k plus 1 times k, the number of dots in this rectangle. And consequently, if I just divide by 2, I get the formula that I'm interested in. The sum of n goes from 1 to k, is k plus 1 times k over 2, right? It's half of the number of dots in this k plus 1 by k rectangle. A big part of the joy of mathematics is that the same ideas can be presented with very different clothing. In this case, we're seeing really the same argument, but presented both algebraically and geometrically.